ARLArena, a unified framework for stable agentic reinforcement learning by researchers from UCLA and UW-Madison.
Agentic Reinforcement Learning, or ARL, is incredibly unstable, often leading to sudden training collapse. This paper introduces a standardized testbed called ARLArena to dissect the 4 dimensions of policy gradients: loss aggregation, importance sampling cladding, trajectory filtering, and advantage design. They found that token-level tolerant clipping causes collapse due to an accumulation of negative advantage sequences with low importance sampling, or IS ratios. The solution is sequence-level clipping combined with fine-grained advantages and dynamic filtering.
The researchers combine these insights into a new algorithm called SAMPO, which stands for Stable Agentic Multi-turn Policy Optimization. Applying SAMPO to a small 4 billion parameter model, Qwen3, achieved a 92.72% success rate on the ALFWorld benchmark, completely destroying massive proprietary models like GPT-5.2 at 51.56% and O3 at 56.25%.
That is a massive leap forward.
Welcome to this deep dive on AI paper podcasts. This is the YouTube series where we summarize AI and tech papers, making sure you stay up to date with the absolute bleeding edge of machine learning research.
Yeah, and today we are really tearing into the nuts and bolts of Agentic RL.
Right, so if you are an ML engineer or a researcher who has, ever tried to optimize an agent for web navigation or embodied tasks, you already know the pain here.
Oh, absolutely.
You leave a training loop running overnight, everything looks completely fine.
And you come back in the morning, and the policy has just spontaneously collapsed.
Exactly. It's just outputting blank tokens or repetitive gibberish. We all know that RL works phenomenally well for static reasoning.
Right. Think DeepSeek R1 or OpenAI's O1 models.
Yeah, applying RL to math or coding problems where the environment just doesn't change, it creates these massive leaps in reasoning. But moving from static to multi-step dynamic environments introduces a whole host of compounding challenges.
It really does. Because the jump from static to dynamic is, well, it's essentially a jump into a chaotic, non-stationary state space.
Right.
In static RL, the model generates an answer, gets a reward, and updates. The state itself doesn't react to the model.
It's a closed loop.
Exactly. But in Agentic RL, the agent takes an action, the environment changes state, and then the agent has to react to that newly generated state.
Which introduces so much variance.
Exactly. So if your agent makes a microscopic suboptimal choice in, say, step 2 of a 50-step web navigation task.
Like clicking a drop-down instead of a text box.
Exactly. Then the DOM tree it sees in step 3 is entirely different from what it should have been.
Right.
This creates a severe distribution shift. The state space the agent finds itself in later in the rollout looks absolutely nothing like the distribution it was originally trained on.
Which makes credit assignment a total nightmare.
Oh, yeah.
It's basically like playing a 50-move chess game against a grandmaster, losing, and only being told, you lost at the very end.
Right. You have no idea what went wrong.
Yeah, you have no idea if your opening was fundamentally flawed or if you just blundered on move 49.
Exactly.
And when you combine that incredibly sparse reward signal with invalid actions that actually break the simulation.
Like outputting a malformed JSON.
Right. You get degenerate rollouts. It makes ARL training runs notoriously difficult to reproduce. You can run the exact same code with the exact same seed, and one run magically converges while the other just completely falls apart.
And that irreproducibility, that is the core roadblock the researchers tackle first in this paper.
Because before you can test new algorithms, you have to build ARLArena.
Right. You simply cannot measure the mathematical impact of a new gradient technique if your baseline is just spontaneously collapsing due to environmental noise.
Impossible.
So they engineered a 3-step stabilization recipe to create a clean, reproducible testbed.
Let's walk through those steps.
Sure. So step 1 is behavior cloning, or BC.
Right.
Rather than starting RL from a generic instruction-tuned state, they initialize the policy within a reasonable behavioral manifold.
So they take the base Qwen3 model, let it interact with the environments, keep only the high-scoring traces, and then perform self-bootstrapped supervised fine-tuning on those exact traces.
Exactly, which gives it a solid foundation.
And that brings us to step 2 of the baseline, which addresses arguably the most common failure mode early in training, which is formatting.
Oh, formatting is huge.
Right. If you're dealing with an ATI or a strict simulation environment, the model can generate a brilliant, totally logically sound plan. But if it forgets a single bracket in its JSON output,
The environment throws a syntax error.
exactly, and the gradients from that entire interaction are completely trash.
Right, they're useless.
So to fix this, the researchers implemented a strict format penalty and heavily relied on KL regularization.
Because in a multi-step agentic loop, if your policy drifts even slightly from the base model's syntax, your KL divergence just explodes.
Yeah, the model essentially forgets how to speak the environment's language. So KL regularization keeps the policy tethered to reality, while the format penalty ensures the model actually learns the syntax before it even tries to learn the complex reasoning.
Which is such a crucial ordering of operations.
Definitely.
And then following that format anchoring, step 3 is a rigorous policy optimization-specific hyperparameter grid search.
Right.
They establish a bedrock that is so solid that any subsequent collapse in training can be definitively attributed to the algorithmic changes themselves.
Not just random environmental noise.
Exactly. This allows them to systematically decompose the standard policy optimization gradient into 4 completely orthogonal dimensions.
Okay, let's really get into those dimensions, starting with dimension 1, which is importance sampling, or IS, clipping.
Right.
For a bit of context for you listening, if you're using standard GRPO, which is Group Relative Policy Optimization, you are relying on token-level hard clipping.
Which is very aggressive.
Yeah, it aggressively truncates the gradient update if the new policy deviates too far from the old policy. It's a hard mathematical ceiling designed to keep updates within a safe trust region.
Right, and the natural assumption in the RL community has generally been that softening this hard ceiling might lead to smoother, better learning.
Which makes intuitive sense.
It does. And the paper explores this in findings 1 and 2 by comparing sequence-level clipping methods like GSPO against what they call tolerant clipping methods like SAPO and CISPO.
Right, where tolerant clipping uses temperature-controlled gating or stop gradients instead of that hard mathematical cutoff.
Exactly. The theory is that being gentler with the gradient will preserve more of the useful signal.
But the data they present shows the exact opposite.
It really does. In ARL, tolerant clipping reliably induces catastrophic training collapse.
Which is so counterintuitive. Why would a gentler clipping method suddenly cause the model to destroy its own policy?
The paper diagnoses this beautifully, actually. The collapse isn't random. It is driven by a highly specific accumulation of out-of-bounds tokens.
Okay, break that down.
So specifically, these are tokens originating from trajectories that have a negative advantage, meaning the rollout failed or just performed worse than the baseline.
Right.
And, crucially, they have an important sampling ratio of less than 1.
Okay, so conceptually, an IS ratio less than 1 just means the current policy already wants to take this action less than the old policy did.
Exactly. It is a bad action, and the model already knows it's a bad action.
So with tolerant clipping, instead of throwing that gradient completely away because it's outside the trust region, you keep a fraction of it.
Yes.
It's basically like a leaky faucet filling up a bucket with bad gradients.
That's a great analogy. Over a long multi-turn sequence, these tiny, seemingly harmless updates from negative, low-probability actions start to accumulate. They build up in the lower bound portion of the clipping range.
And eventually that bucket just overflows.
Right, destabilizing the gradient entirely and pushing the policy into a degenerate state.
And the empirical evidence they have for this is stark. When they ran the ALFWorld embodied environment using the SAPO tolerant clipping method, the success rate plummeted to 25.16%.
The model practically forgot how to solve the tasks entirely.
But what's really fascinating is how they actually prove this hypothesis.
Yes, the sequence masking intervention.
Exactly. They implemented a targeted intervention called sequence masking. They basically built a mathematical tripwire. If a trajectory has both a negative advantage and a low IS ratio, they mask it out.
They just zero the gradient for that specific toxic sequence.
Right. And the moment they applied sequence masking to SAPO, the success rate instantly shot up from 25.16% to 76.92%.
Which is a massive jump. And that delta proves unequivocally that token-level constraints are fundamentally insufficient for agentic RL.
You have to use sequence-level clipping.
Like GSPO does.
Right, to prevent that toxic accumulation and maintain stable, monotonic improvement across these really long, multi-turn horizons.
Exactly, which moves us nicely from clipping to dimension 2, which is advantage design.
Right, this leads us to finding 3 in the paper. The standard approach in RL is to calculate the advantage at the trajectory level. Did the entire 50-step rollout succeed or fail?
But as we established with the chess analogy earlier, for long horizon tasks, a trajectory level reward signal is just too sparse to be actionable.
It is. So to solve this credit assignment bottleneck, the researchers evaluated GIGPO, which stands for Group-in-Group Policy Optimization.
Right, and GIGPO moves away from a monolithic trajectory score. It introduces a hierarchical advantage.
So it calculates the overall trajectory level score, but it pairs that with a step-level relative advantage.
Exactly. This gives the model fine-grained feedback on its intermediate actions. And they also integrated EMPG, or entropy modulated policy gradients.
Let's break down the mechanics of EMPG because it's a very clever use of uncertainty. EMPG dynamically scales the gradient based on the policy's own entropy at each individual step.
In plain English, it looks at how confident the model is.
Right. If an action leads to a state with high future clarity, meaning the model is highly confident about what to do next, EMPG rewards that action more heavily.
And by incorporating this stepwise environment-level information into the advantage design, they saw really consistent improvements in both training stability and the final success rate.
Which naturally leads us into dimension 3, dynamic sampling or trajectory filtering.
Right.
This is where the mechanics of agentic RL diverge wildly from static reasoning tasks. If you are training an LLM on a math benchmark like TI-Marth, dynamic filtering is standard practice.
Oh yeah, you simply drop the rollouts that fail to reach the correct answer and only train on the successful trajectories.
Exactly. But the researchers found that applying this exact same filtering to agentic RL creates some very counterintuitive behaviors.
It really does. Finding 4 specifically highlights that dynamic filtering actively hurts standard GRPO, but it significantly helps GIGPA.
And to understand why, we have to look at how these models actually learn to format their outputs.
Right. Early in the training process, a massive percentage of an agent's rollouts are complete failures.
But they aren't failing because the reasoning is necessarily flawed.
No, they're failing because the model hallucinated an action that isn't in the API, or it output a string instead of a JSON object.
Formatting errors.
Exactly. Standard GRPO actually relies on these all-failure rollouts to learn the formatting rules.
Right, because GRPO calculates advantage relative to a group of rollouts. So if the entire group fails due to formatting errors, the format penalty provides a massive, unmistakable negative signal across the board.
And that synchronized negative gradient forces the model to quickly adapt to the correct syntax.
But if you introduce dynamic filtering and strip out all those failed rollouts, you are effectively hiding the format penalty from the model.
Exactly. Without those boundaries, GRPO drifts. It forgets how to format its outputs, and the training degrades.
Yet GIGPO survives the exact same filtering process.
Because GIGPO utilizes that hierarchical step-level advantage we just discussed. It possesses a much richer variance in its advantage signals at every single step of the rollout.
Right. Even if you filter out the catastrophic trajectory level failures, GIGPO generates enough fine-grained, localized signal to keep the format learning completely stable.
And once that formatting bedrock is secure, GIGPO can fully benefit from the dynamic filtering, actually removing the degenerate reasoning path.
It's a perfect illustration of how algorithmic dimensions in RL do not exist in a vacuum. Your advantage design directly dictates whether your filtering strategy will succeed or just cause a collapse.
Completely agree.
Just to quickly touch on dimension 4 before we move to the final algorithm, which is loss aggregation.
Right.
The researchers tested sequence mean token mean versus token mean aggregation.
And they found that compared to important sampling and advantage design, loss aggregation had a relatively limited impact on the overall success rate.
Which is honestly a really useful finding. It allows engineers to stop obsessing over aggregation methods and focus their compute budget on the dimensions that actually move the needle.
Exactly. So bringing all these isolated findings together, the researchers engineered the ultimate solution, SAMPO.
Stable Agentic Multi-turn Policy Optimization.
Yes. SAMPO unifies sequence-level clipping to prevent gradient accumulation, turn-level fine-grained advantage to solve the sparse reward problem, and dynamic filtering to clean up the optimization landscape.
And the performance jump is substantial. SAMPO achieves an average 25.2% improvement over the standard GRPO baseline across their tested agentic tasks.
It delivers a stable monotonic improvement curve. It completely avoids the catastrophic drops that plague other methods.
But the paper goes beyond algorithmic design. They also tackle a severe infrastructure bottleneck that rarely gets discussed in academic papers, but constantly haunts ML engineers in production.
Oh, off-policy staleness.
Yes, off-policy staleness is the harsh reality of training large models on modern hardware.
Mathematically, policy optimization algorithms like PPO or GRPO assume they're learning from fresh data generated by the current policy.
Right. But in practice, you can't run a single rollout, update the multi-billion parameter model weights, and then run another rollout.
No, it would leave your GPUs sitting idle 99% of the time.
Exactly. To saturate the hardware, you have to generate a massive batch of trajectories, store them in a buffer, and then perform multiple mini-batch gradient updates over that data.
Which introduces a massive synchronization problem.
Yeah. As you perform those mini-batch updates, your policy is evolving. By the time you reach the end of your buffer, you are updating your newly evolved policy using trajectory data that was generated by an older, stale version of the policy.
It's like trying to navigate a shifting maze using a map that someone else drew 5 minutes ago. The walls have already moved, but you're still making decisions based on outdated information.
That is a perfect way to visualize it, and the performance penalty for this staleness is severe.
Right. The researchers quantified this on the TIR math task.
Yeah, when they used a low off-policy ratio, meaning a smaller batch size of 128.
Which keeps the data fresh but underutilizes the hardware.
Right. The model achieved an 87.34% accuracy on the pass-set32 metric. But when they scaled up to a high off-policy ratio, using a batch size of Pentraining 24 to actually maximize GPU throughput, the accuracy dropped all the way down to 74.99%.
That is a huge drop.
Yeah.
And when you transition from a single-turn math problem to a multi-turn agentic setting, that staleness problem compounds exponentially.
Because one rollout isn't just one sequence, it might be 30 distinct actions and environment transitions.
Exactly. Turn-wise decomposition drastically inflates the sheer number of samples sitting in your buffer, aging while the policy updates.
It's a stark reminder for you listening that your infrastructure constraints, specifically how you batch your rollouts for efficiency, are directly harming the reasoning capabilities of your agents.
It really forces a difficult trade-off between hardware efficiency and algorithmic stability.
It does. But if you can navigate that trade-off and implement a stable training recipe like SAMPO, the scaling results are phenomenal. The benchmarking section of this paper is really the ultimate David versus Goliath test.
It is. They evaluated SAMPO on ALFWorld, which is a complex embodied AI environment, and WebShop, a highly dynamic multi-turn web navigation task.
And they took the Qwen3 4 billion parameter base model, which is tiny by today's standards.
Very tiny.
They ran it through their behavior cloning stabilization and then post-trained it using the SAMPO algorithm. On ALFWorld, that 4B model hit a 92.72% success rate.
Which is incredible. But what's really surprising here is the delta in performance compared to the frontier models.
Yeah, you've got OpenAI's GPT 5.2 sitting at 51.56% on that exact same benchmark.
And even O3, the state-of-the-art reasoning model, only scored 56.25%.
And to add context to that O3 score, it wasn't just a simple zero-shot attempt.
No, that 56.25% was achieved using highly complex multi-agent system debate strategies at inference time.
Right, where multiple agents argue and cross-examine each other to find the optimal action.
Exactly. Despite spending all that test time compute, it still trailed a 4 billion parameter model by nearly 40 points.
And furthermore, when the researchers scaled SAMPO up to the Qwen3 8 billion parameter model, they maintained those exact same massive, stable gains.
This fundamentally challenges the current industry narrative.
The idea that you need massive parameter counts and heavy inference time compute to solve agentic tasks.
Right. It reframes how you should be allocating your compute budgets.
Yeah, the training recipes, the clipping strategies, the hyperparameter grids, these aren't just minor optimizations to make a loss curve look pretty. They mathematically define the feasible region where advanced reasoning policies can actually emerge.
If your baseline RL optimization is mathematically flawed and prone to toxic gradient accumulation, no amount of complex inference time engineering is going to save your agent.
Scale cannot replace stability.
It really can't.
So, for the engineers listening who are actively building out multi-turn RL pipelines, the actionable takeaways from ARLArena and SAMPOs are crystal clear. Token-level clipping is a trap in ARL. You need sequence-level clipping to prevent out-of-bounds gradients from destroying your policy.
And you must implement fine-grained, stepwise advantages to give your model actual signal in long-horizon tasks.
And you absolutely cannot ignore your formatting constraints. Strict formatting penalties and KL regularization are mandatory before you even attempt to optimize for reasoning.
Applying all of this brings us to a highly provocative realization about the future of interaction data.
Yeah, let's hear it.
This paper proves that stable ARL actually unlocks scaling laws for multi-turn environments.
Right.
If a remarkably small 4 billion parameter model equipped with SAMPO can outperform GPT 5.2 and o3 by such a wide margin on complex agentic tasks, what happens when this exact stable RL recipe is applied to a 100 billion parameter foundation model?
That is the real question.
Will inference time compute strategies, like these expensive test time debate setups, become completely obsolete for agents if the base policy is actually trained correctly in the first place?
It certainly makes you wonder how much compute the industry is currently wasting trying to fix poorly trained agents at runtime, rather than just fixing the RL loop itself.
Absolutely.
Something to ponder as you review your own training pipelines. Thanks for joining us for this deep dive into ARLArena and SAMPO here on AI Paper Podcasts. We will see you next time.